Alright, in this chapter, chapter 13, we are going to look at equilibrium. Now, it's related to our chemical kinetics. Kinetics applied to the actual speed of a direction, or speed of a reaction. Now, it's specifically in the arrow of a reaction. So we have reactants go into products. Kinetics dealt with the speed that this happens. Equilibrium deals with the fact that reactions are also reversible. And we want to look at the relationship to that forward and reverse reaction. And we want to know when it reaches equilibrium. Equilibrium is simply when the rates of those two arrows are exactly the same. Now, there's plenty of times the rate going forward is far faster than the rate going backwards. And in that case, you'll get mostly products. But sometimes you get a pretty even mix of the products and reactants. And the reaction never really goes to completion, in the sense that it never goes totally to products. It actually stays in a nice little equilibrium between the products and the reactants. Now, it is dynamic. When you get a reaction that's equilibrium, it's not that the reaction stopped. It's still reacting. It's just that it's actually going forward and backwards at such the same rate that the concentrations stay the same. All right, so picture-wise, what does this mean? A good example of a simple reaction that actually reaches equilibrium and actually contains both products and reactants is this one here with N2O4 going into NO2. Turns out the NO2 is kind of like a brownish color. So the colorless N2O4 will gradually, the container will gradually get darker. Yet, even at the end, when it actually appears like the concentrations stop, there's still going to be plenty of N2O4. It's just that the N2O4 is being destroyed at the exact same speed the NO2 is forming the N2O4. Alright, so we're going to need to study this. Now, we're actually going to use this thing called an equilibrium constant to relate those. Now, it is a product, or it is a result of taking the rate constants from our previous chapters and doing a nice little ratio of them. Now, fortunately, we don't have to actually study the actual rates to get this. We actually will be able to study the concentration of our products and reactants. And before, when the N and M were dependent on the rate law and dependent on experimental evidence, we'll find that if we're an equilibrium constant, that capital K, we can actually determine that rate equation from the balanced equation. But we are going to definitely relate this equilibrium to the concentrations of our products and reactants. Alright, so what does that look like? Technically, we're going to have different size K's that tell us more about what's going on in the environment. So a small K, and think about the K being a product of a reactant type thing. If you had a small fraction, that implies that the bottom number is bigger, right? Or the top number is small. Well, that does imply in this case that most of your reaction is still reactants. The large K means the exact opposite. The products are more, so we have a lot more products. And intermediate, right around 1, so if the K is right close to 1, that really does mean that the ratio of the products to reactants is about equal to one another. Now, these are never negative numbers. These are always just larger than 1 or smaller than 1. Alright, to get that reaction quotient, we actually can, in this case, look fully at the balanced equation. The balanced equation, using the coefficients, the coefficient turns into the powers. Kind of like our elementary reactions did in the previous rate equations. But this time it doesn't matter. Any balanced equation, you can turn it into the reactant quotient and just put those little subscripts there. Now, when this particular reaction reaches equilibrium and the concentrations freeze, Q becomes K. And we might actually change that written to say something like this instead. C of C at equilibrium, D of D at equilibrium, A at A equilibrium, and if it's at equilibrium, this product quotient becomes K. Any other time, it's just a value that tells you that the reaction is still moving forward or backwards. And it's kind of neat. If the Q is larger than K, we do know that we have too many products. So the reaction is going to end up going backwards. And we'll see this as we build up on it. So here's that reaction we actually had. The N2O4 going to NO2. And we got various different reaction component starting ingredients. So basically we'd have one where it's nothing but N2O4 and another one where it was nothing but NO2, and we let it go forward. Now, we were able to do a calculation using those numbers to get a product quotient. And of course we get 0 because anything zero over anything is 0, and anything divided by 0 is infinity. So these are almost useless right now, but it is a small value. That's the smallest it can be, so we know the reaction must be going forward. That's as large as it can be, so we know the reaction must be going backwards. And the size of those will actually come in handy in just a second. Alright, so these are some actual data that we get when we let them go to equilibrium, and they're totally different from one another. But when we plug them in this equation, we get the same value. That is our K. And even if we start with some of both and let it go, we'll get that same 10.4. Now the neat thing is, this time if we have a Q and we know what our K is, since this Q is smaller than K, we know this reaction is actually going to go forward. And same thing happened here. This Q is also smaller than K, so we're definitely going forward there as well. But no matter what, we'll get the same K at equilibrium. Now this difference is mathematical rounding, so that's why it is different there. But it is actually acceptable that it's off that little bit. Alright, so here's what we're seeing on all those things. The rates will change over time, but eventually get to the point where the concentration appears to be fixed. That's equilibrium. Okay. Alright, let's figure out what a Q would look like for this particular reaction. Now, got a small problem here that you're not going to see on the actual test. I've given an unbalanced reaction right now. Now, reason that's not going to happen on the genuine test is because there's more than one way to balance an equation now. Remember in general chem or in intro we said you couldn't use fractions. Well, we're allowed to use fractions now. So let's assume we wanted to balance this where there's exactly 1 mole of N2O5 being used up. I would need to have 2 of these to get the 2 nitrogens, and I have 4 and 6 oxygens, but I only needed 5, so I'd have to use a fraction there. However, if I balanced it per the old school way, that would be 4, where I can't have fractions, I would end up with something like this. And both of these are balanced equations. Depending on how you balance it, you're going to get a different Q, because the Q here is going to have our products over our reactants. This Q has all the same components, but our superscripts are going to be different. So technically our answer for this, our product quotient, is dependent on the balanced chemical reaction. So you are going to be given balanced equations always here, because depending on how you balance it, it's going to change what the K is at equilibrium. Alright, and we're not going to bother to do that one because it does the same type of thing. Alright, here are 2 that are balanced equations. So I have N2O2 going to NO, followed, and I got a second reaction where NO plus O2 goes to NO2. Alright, it's actually a mechanism. It's those 2 elementary steps going together. We want to actually come up with a Q for the overall process, and we want to show that it's comparable to these 2 equations. Alright, what I mean by that, you notice how this NO2 is really one of those reactive intermediates we talked about? It's actually used up totally in that second equation. The overall process is the N2 gas and 2 oxygens go to form, with equilibrium, 2 NO2 gases. So we just combined them together. Well, that is the overall process. I'd love to know what the K is, and I'd love it to be somewhat dependent on those 2 up there. Something we need to do to those 2 to get them to combine. Well, let's see if we can figure out what that might be. And what we're going to do, we're going to come up with what the Q for this equation looks like. So the Q for the overall equation is products. I'm going to leave the phases off since they're all gases. Over reactants. Products over reactants. That's for that overall one. Well, let's see what the Q for 1 is. I'll put it up here. And that is N2 and O2 and NO squared. And then Q2 is NO squared, O2, and NO2 squared. Alright, what could I do right here to get these two to be equal to that? Well, if we're clever enough on math, we could see that these would cancel if I multiply them. And the two O's would actually combine. That would be it. So it turns out when we add equations, since we just added these, we can multiply the Q's. And that always works. The Q's will just multiply together anytime you add equations. Alright. Some other manipulations we've sometimes done, I don't want that, is I might have actually taken the original equation and changed coefficients or reversed it. Let's see how that affects the Q. Alright, so got our equation, and we're going to come up with a Q for it just so we have it written as practice. So it's going to have the NH3 squared all over N2 and H2 cubed. Products over reactants. Alright, let's look at A, and let's come up with a Q for that one. Products is the NH3, and it's going to be the 2 to the 2/3, and on the bottom is the N2 to the 1/3, and just a single hydrogen. All they did was they changed that equation so the hydrogen, it was just 1. Or you could say we took the original Q and or the original equation and divided all the coefficients by 3. Alright, but what would we need to do to the coefficients on this? So what would we need to do to this Q to turn it into this one? Well, it's actually just as simple as raising everything to the 1/3 power. So since we're multiplying all the coefficients in this equation by 1/3, we'd raise the K to the 1/3 power. And so the K for A is, let's see what it is, 2.4 times 10 to the -3rd raised to the 1/3 power. And we get a K of 0.13. Alright, now let's look at the second equation, B. You notice how it's reversed? And the coefficients are changed, they're divided by 2. Alright, let's see what that Q actually looks like, and so we can see what we might need to do to actually manipulate this equation up here. So that's to the 1/2, H2 to the 3/2, and NH3 to the 1. Alright, that's all well and good. But now I have to ask, what are we going to do to this equation, to our original equation, to turn it into this? Well, the 1/2 is probably kind of obvious, because that's what's going to get all the coefficients to be right, the superscripts. But how do you flip an equation, or flip a fraction? Yeah, -1/2. So this is kind of neat. To get that second K, I'm going to take that 2.4 times 10 to the -3rd, and I'm going to raise it to the -1/2 power, or yeah, -1/2. And I get that K is 20. All right, now this is why I have to give you a balanced equation, because clearly we can balance it different, and yet these k's are not the same. You have the k that you're given is based on the balanced equation. Same as the q, it's based on a balanced equation. All right, another weird thing that pops up. This is a very neat reaction. So what we have going on here is calcium carbonates decomposing. So it's a solid, and when you heat that up, it turns into calcium oxide, lime, and CO2 comes off. All right. Technically, it has a Q, right? So let's say it's an equilibrium, because it is a reversible process. If you take lime and leave it outside, it's going to absorb CO2 in the air. If you take calcium carbonate and heat it up, it's going to turn back into lime and carbon dioxide. All right, but it has a Q that has all these components in it. All right, but I have an odd question for you to see if you remember anything tricky about solids. All right, think about this. Don't solids have fixed densities? Yeah, for the most part they do. Well, let's think about that density, and let's think about units we could turn it into. If we knew the density of calcium carbonate, couldn't we figure out how many moles per cubic centimeter there is? Could we turn grams into moles? Yeah. And couldn't we convert cubic centimeters into liters? Yeah. All right, here's the weird thing. Solids that have a fixed density have a fixed concentration. These concentrations never change because it's a solid. Yet the reaction will go forward. It will change. It just doesn't, it's not dependent on anything to do with the amount of the calcium carbonate or the calcium oxide. So it's kind of interesting. What we're going to do, what we're going to say though, is when we're coming up with a Q, you're leaving solids out. Solids, since they don't change their concentration, they're never included into reaction quotients. All right, so this is a summary of the things that we've kind of been talking about and done with them. And it's a table from a different textbook than yours, but you have one similar to it. Okay, next one we're looking at is a weird one. We have the ability to do pressure-based Ks. So rather than just concentration, it might be pressure. So like this equation, if I want to do a Q based on concentrations, it would look something like this. NO2 squared over NO squared and O2. Perfectly fine. But a Q based on partial pressures also happens. And it would be the partial pressure of the NO2 squared all over the partial pressure of the NO and the partial pressure of the O2. And there's a 2 there. So technically it looks the same, it's just different notation. But the units would technically be different. So concentrations are always molarity. Pressures could be atmospheres or torrs or just pressure units. So the Q's would not be mathematically equivalent. Fortunately, they're convertible. And that's what they're looking at here. Technically, think about our gas law, P equals nRT. We can manipulate this. And what's what they're doing? They're getting this N over V all by itself. And let's think about it. Why would they do that? Well, N is moles, volume is liters. That's molarity. So molarity of a gas is proportional to the pressure divided by the R and the T. So here's something neat. If I had a bunch of pressures and I wanted to convert them into this Q, I theoretically could just divide all these by RT and I'd have this. Alright, so because of that, we have this cool little relationship between these two. Excuse me. And what I mean by a cool little relationship, a K in terms of pressure can be found to be related to a K in terms of concentration by taking that R and T that we just did and raising it to a delta N. And the N is just the difference in the number of moles. Because you see how these RTs, those and those would cancel out? But this one would still factor in. So you wouldn't have to do it in all the cases mathematically. So what we do to get it in there, we add up the number of moles of gases as products and all the moles of gases as reactants, and we just do a subtraction there. And this one is 3 minus 2. or 2 minus 3. Sorry, no, it is 3 minus 2, isn't it? Yeah, 3 minus 2. Okay, let's do something with these. We're going to look at that particular reaction there with Kp and a Kc for the reaction we just talked about. Now, we're not actually going to come up with a new equation. We're just actually going to plug it into that equation we just had up on the screen. So Kp equals Kc times RT over delta N, or to the raised to the delta N. So our Kp is 2.1 times 10 to the negative fourth. We're going to solve for Kc. Our R is our gas constant R. And our temperature is the temperature in Kelvin. And our delta N in this case is, we only have 1 mole of gas here, so 0. No gas over here on the reactants, minus 1. So, calculation-wise, 0.08206 times 1,000 raised to the negative 1. And we're going to take 2.1 times 10 to the negative fourth and divide it by that number. Our Kc is 0.017. Now, fortunately, this doesn't happen much. More often than not, we're going to use Ks in terms of concentration. And even if we have gases, we typically calculate their concentration rather than use their partial pressures. And actually, everything we do after this is going to be based on Kcs, so concentrations. All right, let's do something with the Kcs with an actual equation. Turns out, if we actually are given a set of reaction conditions and we're given a K, we can actually tell from those numbers if the reaction is at equilibrium. What we're going to do is we'll just calculate a Q, or the product or reactant quotient. And if it's equal to K, we are actually at equilibrium. If it's not, it's telling us if the reaction is going forward or backwards. Let's do that for a real problem. So this is our give me question that we've been dealing with. The N2O4 and the NO2 give you a Kc in this case. And I've given you some starting components. I just want to know if it's at equilibrium. All right. To do this, we're going to write this out a little bit more than I need to. Once we get comfortable with this, we can actually write these a lot easier. I'm going to create what we're going to call an ICE table. ICE table is just going to list our initial concentrations, change if we have any, and then what the concentration is at equilibrium. We're not going to fill out this entire table with this, but we're saying at some point, we're going to tell these our initial amounts. So we're going to say this was 0.12 molar, and this is 0.55 molar. And do keep in mind, your ICE table should always have molarities in them. All right. This equation has a Q associated with it that's based on that balanced equation. Now, all we're going to do to figure out if we're going to change the reaction is plug in and solve for a Q. And what do we get here? .555 squared divided by 0.12. The Q for this at that point is 2.5. Alright, now looking at the K, this is definitely larger. So it's saying this quotient is too big. It needs to get smaller. The only way that's going to happen is for this to go backwards. Now, technically that's all we need to know on this. Is it at equilibrium? No, not at equilibrium. And so if it's not, which direction is it going? It's going in the reverse. Now, what we're going to do in this class from here on out on this chapter is figure out how far. So we do know from looking at this must go down and this must go up. That's how it's going to change. we're going to actually use variables. We're going to say this is going to go up by amount x. And if this goes up by x, this must go down by twice that because it uses up 2 of these for every one of them. So whatever we're at equilibrium, it's going to have that x added to it, and this is going to have an x added to it. Alright, theoretically, I'm going to put this up here, we could solve for x, because we know at equilibrium that Q is 0.21. Theoretically, now that we've had our college algebra, we could solve for x there. We're not going to do it quite yet, but that's what we are going to introduce. We're going to actually introduce simpler ones at first. Alright. Here's a table that's going to be a little bit easier to complete. So I give you in a similar type of idea. I've given us our equation, and we are going to set up an ice table just like that previous one. And in this case, I told you how many moles there were at first, and I told you the volume. Remember how I said that we wanted this to be molarity? We're going to calculate the molarity, and that's what's going into our chart. Well, this one, I wouldn't need a calculator for this, but I'm going to type it in anyway. So, my concentration of HI gas initially is 0.1 molar. Now, you notice how it doesn't mention anything at all about the H2 and I2. Because they're not mentioned, we're assuming they are 0. Alright, now, we can also calculate what our Q looks like, and we could calculate it right now, but actually I don't think that's necessary to know which direction this reaction's going. And why isn't it necessary? I don't have any products. There's no way it's going backwards. This must go forward. Alright, so this must go up, down. This must go down by a certain amount. I'm going to put 2 in front of it, so 2x. This must go up by that amount, and so would this. So equilibrium, this is 0.1 minus 2x, this is x, and this is x. Alright, if you notice, it wants us to calculate the k. It helps us get our x, this x, because it tells us at equilibrium the HI concentration is 0.0778. So that 0.078 is actually equal to 0.1 minus 2x. We're going to use that to solve for our x. So, 0.078 minus 0.1 divided by negative 2. And we get our x is 0.011. So, now to calculate our k, we're plugging values in. Our equilibrium amount of H is x, 0.011. Our equilibrium amount of I is also 0.011. And the HI in the bottom is that 0.078 squared. So, take that number we just did, multiply it by itself, and divide by 0.078 squared. And we get a K of 0.020. No fancy math done. Just basically solve for x and then plug in your x. Alright, what else can we do? Alright, this is an interesting one. I've given you a balanced equation, told you what our equilibrium amounts are. Alright, we are going to set up an ice table because that's a good practice to be in for all of these type of questions. It helps you organize the amount of data that I've given you because we do give you a lot of these. Alright, now if we were to in a rush and just read that, we might think these are our initial values and write them down, but you notice how it says these are equilibrium values? I'm going to skip right down here and put them in for equilibrium values. So I give you moles, but remember how we want molarity in our ice table? We're going to take this 0.26 moles for our CO, we're going to divide it by 0.32 to get a molarity. So 0.26 divided by 0.32 tells us that the CO molarity is I'm going to put all these digits down, 0.812625. And let's see, hydrogen is 0.091, 0.091 divided by 0.32, and that is 0.2844. And finally, the CH4 is 0.041 divided by 0.32, and that is 0.1281. Now, it wants to know the H2o at equilibrium, and it gives us the K. Now, the reason this works is because we know our Q equation, because we have that balanced equation. We are just going to plug some stuff in. So our K is 0.26, our CO is the 0.8125, our H3 is the 2844 cubed, CH4 is 0.1281. We are going to solve for this. Well, that's not so bad. Let's see, what do we get here? So I'm going to do 0.88125 times 0.2844 cubed. Can divide that by 0.1281. Oops, I dropped my decimal. Now, I'm going to do that nice little identity where I can swap these two. So I'm going to divide this by 0.26. And that value right there is my missing concentration. My H looks terrible. What is that? 0.56. All right, let's actually try to do something a little bit more complex. All right, now it doesn't look like it at first, but let's actually organize ourselves and get ourselves an ice table going. And I have 0.25 moles in a 0.125 flask. So this is 2 molar, and this is 2 molar. Yeah, I will calculate that, just so you see where that came from. 0.25 divided by 0.125. Convert that to liters. And it doesn't say anything at all about these, so I assume they are 0. And because they are 0, this reaction is going forward. So equilibrium, this will be 2 minus x, this will also be 2 minus x, this is x, and this is x. And our Q for this reaction is CO2 and H2 all over CO and H2O. Alright, so far so good. This looks very similar to what we just did. But I've given you a K, and I want to know what the equilibrium composition is. So I want to know essentially what the x's are so we can solve for each one of these. So let's look at what this would turn into. 1.56 equals x times x all over 2 minus x and 2 minus x. Alright, without actually explaining that, do you see how this turns into a quadratic equation? This looks like it could be complex, because a quadratic equation always gives you 2 possible values of x. Alright, this does technically give us 2 possible values of an x, but there's a much quicker way to solve this one. Since this and this are the same, and this are the same, I can actually take the square root of it and get just x over 2 minus x, which removes the possibility of a quadratic equation. But I will have to take the square root of 1.56, since I'd have to do that on both sides. So I got to do that on this calculator by, there we go. square root of 1.56. And I get, that is 1.249. We're just going to solve for this x now. So I'm going to take that and multiply it by 2. And get 2.497 minus 1.249x equals x. So I'm going to move this over here and then divide this then by this value right there plus that 1. And I get an x of 1.11. So my equilibrium concentrations, my CO concentration and the H2O concentration are both the same. It's 2 minus that 1.11. And if I do that, I get 0.89. And the CO2 and the H2O are both just equal to x, which is 1.11. Alright, so we avoided actually any complex quadratic equation by just realizing that and taking square roots. Alright, but what if we can't avoid the quadratic? And that's where this problem is going to come in handy. Alright, so I got this nice little equation. We're going to do the same type of thing. We're going to set up an ice table to organize everything we have in there. Now, I told you we have 5 moles of COCl2 in a 10-liter flask. So this is 0.5 molar. This is 0 and this is 0. So our change says this is going down and these guys are going up. And our Q for this equation is CO and Cl2 all over COCl2. Alright, this is not going to be evenly reducible ever. So we plug it in. I'm going to have 8.3 times 10 to the minus 4 equals x times x all over that 0.5 minus x. This is going to be a quadratic equation no matter what. But we still would like to avoid our solving that and taking time with it. But we can do that in certain situations. This one's an especially good one that we can do this with. You see how small this k is? Remember how small k's basically do say that we don't go forward very far? Alright, so if this doesn't go very far forward, do you expect this x to be very big? No. If that's not very big, is this going to make a big difference here? No, it's still probably going to be pretty close to 0.5. Well, let's actually assume it is. Because that really makes this math simple. So if it stays mostly 5, I could take 8.3 times 10 to the negative 4th and just multiply that by 0.5. And then I can get my square root, my x, by just taking the square root of this answer. Alright. What'd I do? Oh, I did 8.3 times 10 to the 4th. 8.3 times 10 to the negative 4th times 0.5. And now I'll take the square root of that. That's a little bit better. Alright, if we do that, our x is 0.0, what was that, 204. Alright, well, is that a safe bet? It definitely is small, but is it small enough to ignore? What we can do to check it. So this is the x we just actually came up with. We're going to compare it to what we just actually assumed was okay to ignore. So I'm going to take that 204, I'm going to divide it by that 0.5. This is going to give me a rough percent error. See how that's only like 4% error? As long as that's under 5%, under 5%. That's perfectly fine to do. So we are okay doing this. And if that's the case, we can say that our equilibrium concentration of COCl2, we could either say it is 0.5, or you can actually say it's what's that going to be, 48, and do the actual subtraction. And then the CO and the Cl2 are equal to 0.024 molar. The answer is not dead on perfect, because we did introduce some error into it, but it's a very small error. It's probably in that last digit is where the error is, so it's a safe bet to do. We're allowed to do this. Alright, this next slide we're not going to be able to. Only thing I've done was started with a heck of a lot less. So everything else is exactly the same. So the ice table is going to look the same, except this is now 0.01. This is still a 0, this is still a 0, so this is still going down. These are still going up. I need to label my rows. So this 0.01 minus x, this is x, and this is x. Our Q is the exact same as the previous slide. So we're going to set up, and it looks the exact same. So right off the bat, I'm going to try that exact same thing and assume that that x is small, because it is still expected to be small. Let's see what it does this time. 8.3 times 10 to the negative fourth times, this time, 0.01. Now we're going to take the square root of this. Alright, the new x is 0.002, so it is small. But let's compare it to this 0.01 that we assumed was more significant. See, that's like 28% of it? That's way more than 5%. Because of that, this is not a safe bet to use. So you don't want to do that. Alright, so because of that, we actually have to do the quadratic, because we're going to move this over, make this -6, and 8.3 times 10 to the negative fourth x equals x squared. So manipulating again, x squared equals, or x squared plus 8.3 times 10 to the negative fourth x minus 8.3 times 10 to the negative 6, and then we plug that into our quadratic equation. Now if you have a graphing calculator, there's a quicker way. Alright, so what I'm going to do is I'm going to put this into my graphing calculator. So this as in, box it in. And we're going to solve for that x using our graphing calculator. So clear that out. Y equals, I'm going to put this in just like it says, x times x times, oops, another set of parentheses, 0.01 minus x to the negative 1. So that's this whole fraction. Now I'm going to move this over. Minus 8.3 times 10 to the negative fourth. Alright, my equation's in there. If I hit graph, TI does something. I'm not terribly worried about this. All I'm going to do now is try to calculate where it crosses 0. And I know it's somewhere between 0 and the highest x could be is 0.01. That's way too high. And then I'll go back here to the guess and hit go. And look at that. It came up with an x of 0.00250. And that value is dead on accurate, and that's as accurate as it can get. You can just plug, if you can use your graphing calculator like that, you can actually very quickly get all this. No need to worry about the quadratic equation. Alright, let's do another one of these. Got a big complicated reaction here. CH4 and H2S giving CS2 and 4 H's. Alright. Let's set up an ice table. give you 1, 1, 2, and 2, but they're in a 250 milliliter volume flask. So we're going to multiply each of these by 4. So that's 4 molar. This is 4 molar. This is 2 molar, and this is 2 molar. Or no, 8 and 8. All right. The change is not obvious this time because I don't have a 0 anywhere. So my quotient is going to need to be used to get us a Q. And plugging values in, we'd have 4 and 8 to the 4th, and 4 and 8 to the 2nd. 4s would cancel, 8 squared is 64. Alright, Q is huge. K is 0.003 or 0.036. This reaction is definitely going backwards. Alright, so this would go up. This would go up by 2x. This is going down. This is going down by 4x. Fortunately, this is just asking which direction it's going for. So we don't need to actually do the rest. But look how complex this would be. 4 plus 8, 4 plus x, 8 plus 2x, 4 minus x, 8 minus 4x. Ooh, a lot of stuff in there. And if I wanted to solve for k, this is well beyond the quadratic equation because the top alone is going to have an x to the 5th power. That top is going to have 5 roots. This is a very complex polynomial. However, if I wanted to solve it and get the x exactly, you can actually graph this thing. So let's see what that looks like just so you can see that this works. Might encourage you to dig out your graphing calculator. Times 4 plus x to the negative 1 times 8 plus 2x to the negative 2 minus our kc, which is 0.036. If I did all this right, I'll get some crazy zigzag line if it shows it all. Oh, you can see it does a weird little zigzag. I don't care about that. I know my x value is somewhere between 0, as in doesn't go forward, and the largest it could be is 2. Because if this is 2, this goes to 0. So I'm going to calculate a 0 between a value of 0 and the largest it could be is 2. And I'm going to back up here and put my guess back. Yeah, I know it's dropping there. I can see that. So right around there. And it gets an x of 1.55. And we could plug that in and get all of our components. Now, if I were to give you something like this on your test, because I'm not expecting you to be able to be absolutely fast on this, and I don't want you to spend a lot of time, I would probably do something like B. If the CH4 concentration is 5.56, what's the equilibrium of the other things? So had I told you 5.56, if you knew this, 4 plus x equals 5.56, doesn't that give you that x very quickly? Yeah. Alright, so we're not going to do the test that makes you dependent on having a graphing calculator. It's just that the graphing calculator really will help this stuff. You will always be able to use a quadratic equation or reduce the math or simplify the math by taking or assuming there's errors in it. Alright, so this is the whole gist of what we're doing. So right there is our correction for if you want to try to cheat the math and assume there's a little bit of error. As long as there's less than 5%, you are allowed to do that. Now, the answer key for the actual test and the practice test, I've solved the X exactly every single time. So if you ever make an assumption, you're probably not going to get the exact answer I got on the test, but it's going to be close. I'm not going to have a lot of answers that are close to the right one, but there's only going to be one that works out right. But these are all the steps we just did to get those Q's we just introduced. All right. Next little thing we're going to do is we're going to take an equation that's at equilibrium and stress it. What I mean by stress, let's actually talk about an actual reactant going to an actual product, but let's say they're at equilibrium. So if they're at equilibrium and you increase a bunch of A, just add some in, doesn't it make sense that this reaction is going to go forward until we're at a new equilibrium? Yeah. That's what they're talking about this. When we actually increase a concentration, we're going to have the system react to consume it. If we remove one, the reaction is going to shift to replace it. We're going to see something like this. Here's an actual reaction. So phosphorus trichloride and chlorine given as phosphorus pentachloride. And we got some equilibrium values. And look at this. We just added a bunch of chlorine to it. That jacked the concentration up. Because we knew we added this, the reaction is going to work to consume it, so we know it's going to go down. Therefore, both of our reactants are going down, and the products are going up. We could set up an ice table. If we knew what our Q is, we could solve for the X, and that's what they're showing us doing here. We're actually going to react to consume that. Graphically, it might look like something like this. We're at equilibrium. The green, blue, and yellow lines are equilibrium, and then we just jump up a bunch of chlorine into it. The stuff we add is going to be consumed and go away, and the other side of the reaction is going to just increase. Now, typically when we have these questions, we just ask you which direction the reaction is going. We don't have you recalculate. We just want to know what's going to happen to consume those products we had. Something like this. So I give you this balanced equation, and I tell you it's at equilibrium. So what's going to happen to the H2O concentration if we add a bunch of oxygen? Well, let's think about the direction the reaction is going to happen if we add oxygen. If you add oxygen, doesn't it make sense the reaction is going to go forward? Yeah, because it's going to use up that stuff we've added. If that goes forward, what's going to happen to the concentration of H2O? It should increase. All right, O2 added still expecting it to go forward. What's going to happen to H2S? That's a fellow reactant. That should go down. This is different. See how it says removed? We're going to remove this. Since we're removing a component, it's going to go, reaction equilibrium is going to go backwards to replenish what we removed. If it's going backwards, what's going to happen to the O2 concentration? It's going to go up. Now, D's borderline trick question. Why is this not going to do anything? Adding sulfur should actually shift the reaction, right? Well, the reason it doesn't, sulfur is a solid. Remember how solids don't have a concentration? Adding it's not going to affect anything whatsoever. So adding sulfur won't cause the reaction change whatsoever because sulfur is a solid in this case. Alright, that's Le Chatelier principle with components. Turns out volume also affects our equilibrium. At least sometimes. Alright, reason it's only sometimes, the only way that the volume makes a difference is if our reaction is gas phase and there's an imbalance of gas molecules in the products and reactants. What I mean by that, if we assume these dots represent 1 mole of a gas, our reactants have 2 moles. Our products, there's only 1 mole. So as that reaction goes forward, the number of gas molecules decrease. If the reaction were to go backwards, we get more and more gas molecules. All right, since there's an imbalance, adding pressure by changing the volume will affect the equilibrium, in the sense that if you actually increase the volume, decrease the pressure, you're going to favor the side of the reaction that has more moles of gas. In this case, it'd be the reactants. If you decrease the volume and increase the pressure, you're going to favor the side with less moles of gas. So it's not always forward or backwards. The lower volume favors the side with fewer moles of gas. Higher volume favors the side with more moles of gas. So let's think about this. We want to get the most products. So products over here. We want to change the volume to get more products. You see how on A, the only gas molecules are products. So to get more products, we would need to increase the volume so we could favor the side with more moles of gas. All right, on the second one, which side has more moles of gas? Got 3 moles over here, only 1 over here, so the reactants have more moles of gas. So if we want this to go towards the side with fewer moles of gas, we need to decrease the volume. And the last one, volume has no effect whatsoever. Why is that? Got 2 moles of gas and 2 moles of gas. There isn't an imbalance of gas molecules, so therefore the volume would have no effect whatsoever. No change. Alright, last thing in colligative properties has to do with temperature. So, all this text is kind of neat. I want you to actually do this instead. Reactants going to products. If it's an exothermic reaction, heat is a product. If it's an endothermic reaction, where is heat? It's a reactant. Well, let's treat it like a thing. If we add heat to this reaction, won't we go away from the side we add to? Yeah. Alright, so here's what we got. We're starting here with an exothermic reaction because of that negative delta H, so heat is a reactant. How would we increase this by changing the temperature? If we want to pull it towards the side with heat, we would need to remove heat. Next one is an endothermic reaction. Heat's over here. How will we get more products in that case, which is on the opposite side? We have to add heat. Adding heat there forces it to go forward. And then our last one, another endothermic, but we want to increase the one of the reactants. We're removing heat. We're on the same side of the stuff we want to increase, so we're going to remove the stuff and cause the reaction to come backwards. Alright, last thing. Recognize that type of equation? Well, the bottom of the page are the types of times we've used this equation. We've used this type of equation to relate our reaction rate Ks to the activation energy and the vapor pressure to the heat of vaporization. Well, now we're going to say the equilibrium Ks are dependent on the heat of the reaction, and they do vary. And we can do the same type of thing. I'll give you 2 different reaction Ks, 2 different temperatures, and you can actually calculate the heat of a reaction. If I give you the heat of reaction, you can get the Ks. But we're not going to do one of these as a practice problem because we've done plenty of these. Have one on the practice test, and you'll see me work it out if you want to watch that again. All right, last little thing, summary of what we've just covered in this, and we are adding this in here, catalysts. The nice thing about a catalyst, it does change the rates, but since it actually changes both forward and backwards rate, it typically does not affect the equilibrium. It just changes how quickly you get to equilibrium. Alright, last little thing. Fertilizer, ammonia, a go-to kind of necessary thing to feed the population on the earth. This is something kind of neat. This are typical reaction conditions for ammonia. So industrial conditions, very high pressure, 200 atmospheres, very high temperature, 400 degrees Celsius. Weird thing is, at those conditions, the yield for making NH3 from nitrogen and hydrogen, think about it as an equilibrium. And I'll just go ahead and roughly balance something like this. The yield is only in the 40%, so most of it still are reactants. Here's something interesting. That reaction shifts towards closer to 100% when we're at more of normal temperatures and normal pressures. So I wonder why they do it at such high conditions. It really is the rate. It might go to completion at room temperature and such, but it takes too long to get there. So they use this temperature and pressure to actually speed up the reaction, and they don't worry about the equilibrium. They're just going to purify it as it goes along. And it actually ends up looking something like this. So they pressurize some hydrogen and nitrogen in a compressor, and then they have a catalyst bed that helps speed that up. So in this next chamber, you have a mixture of ammonia with hydrogen and nitrogen. This is where it is, but only about 40% ammonia. Well, ammonia, being a very polar molecule, has a much lower vapor pressure or a much lower boiling point than hydrogen or nitrogen, so they just cool it down here. By lowering the temperature, they can actually condense out the ammonia, and the ammonia comes off as a liquid. And then you take the unreacted hydrogen and nitrogen and you just pump it back into the compressor. So even though this only hits 40%, they just keep on going over and over and over. And it's such a successful thing, we consider this guy a brilliant scientist, and yet if you look him up, he's also essentially the father of chemical warfare. He actually helped pioneer the use of chlorine gas on troops during World War I. Alright, that finishes up with this chapter. Going to have a lot of practice with the worksheets and such.